Thank you much for the introduction, especially in memory forensics, just to be more precise. First of all, this is a big pleasure. One more year here. It's like closing a cycle, because like a year ago, I was here doing this speech Saturday, and on Sunday I went home to do some sport, and I was unlucky enough to have an accident, and I had some sick leave for 6 months. So like I had like a rough time. So it's like closing a cycle. Who am I? Many of you know me. I'm Ricardo Rodríguez, professor at University of Zaragoza. I research on performance, security, dependability in system, and binary analysis and forensics. Sometimes some things are like RFID or NFC security, as you have seen in other speeches from me. I'm not alone. We work as a team. This talk is mainly mine, but I have two other people under my academic guard, both Miguel and Daniel. They're studying their PhD, and we are investigating in memory forensics, binary analyze, exploiting and reversing, maybe privacy issues. We're dealing with Tor things, just to make some publicity, because we have open positions. If someone is interested, just let me know. I want to tell you what's this all about. I'm going to tell you what are the current problems regarding malware detection focused on memory forensics. We'll see each of these problems, and we'll see which challenges are posed, and we will see if we can overcome them. I think that all of you have seen any speech about incident response, or you know something about the subject. According to the definition from the NIST, incident response has a series of phases. We have this preparation phase, then detect, analysis, containment, eradication, and recovery, and then post-incident strategy. We have learned from our errors, and we try to solve things so that they won't happen again. We are very focused. Our job is mainly focused on this detect and analyze analysis phase. Incident response. I have seen here Abraham. What is incident response? It's basically to find out what the hell happened. Just saying it flatly. When there has been an incident related to security, it mainly consists in big W's: who, what, why, how, from when, from where, and how long has it been with us. Normally in companies, these kind of incidents are related to malware cases, the presence of malicious software. When someone runs an incident response, normally when recovering those possible evidences, may have two possibilities, which is a computer. It's to run first of all, is run a computer forensics on the computer itself, that is going to the disk and the memory. Otherwise, is to run online forensics. We'll focus on computer forensics and especially in memory forensics. Disk forensics is maybe yesterday it was Lorenzo who talked about this. It just consists in analyzing the hard disk. We run some tools. We get the evidences, and we analyze what we have obtained. In memory forensics for memory, it just consists in analyzing the memory that has been potentially compromised. Of course, you have to keep in mind the differences between both components. Is it difficult or is it easy to access to a disk? Imagine that you have a cloud server. The server has been compromised. How do we obtain or retrieve the evidences from my hard disk? We cannot just disconnect the hard drive and take it away, because it's in the cloud, and we cannot say Amazon, okay, let me grab my hard drive, please. So many cases, the access to hard drives, it's quite complicated, and with memory, could do something. If we think about the limitations that we have regarding memory and storage, it's always more convenient to analyze gigabytes than analyzing terabytes from a time perspective. Especially because the less information we have, the easier the triage, the initial triage will be performed. It will be easier if I have less data to process, of course. Also, we have the problem that there are some data that can be in the memory, like, for instance, encryption keys that may be in that computer's memory, navigation session that may be open in a browser, or maybe the flyless malware, which in the end there's no physical presence, there's no file within the computer, but it stays all the time in the memory. So we have to focus in memory forensics and not just in the hard disk, in hard drive. Question: how is a memory forensics carried out? I take the computer. First of all, I need to dump the system's memory into a file, into a data file. Normally, this file is known as the memory dump. It's dumping, and it keeps a picture and a snapshot of the current status of execution of the system at the moment of the acquisition. Then we take the file off-site of the facilities. We take it to our facilities, to our forensics laboratory, which is very specialized with maximum security measures, complying all the regulations established by American people, and we will analyze it with the appropriate tools. Those tools may be like volatility or recall. Question: what does memory dump contain? It will contain everything, actually. Memory dump will be an endless source to analyze. All the elements that are susceptible to be analyzed in memory forensics are called memory artifacts. Let's say it like that. How do we recover these artifacts? These artifacts are recovered, well, either by navigation through the internal structures of the operating system. There are tools like volatility that you put that thing out profile, those who are used to it. In the end, we are saying volatility where it has some kernel structures in memory so that it can navigate and do whatever it needs to do. Also, we can do a grep for the memory, and maybe we could find some things. What can it contain? It can contain, on the one hand, everything, all the processes that were running at the moment of acquisition. Imagine you are make a control zapper, and all that whole list of process is captured in that memory dumping. Because maybe more, because there are some processes that may be hidden, and that will be revealed in that memory dump. All the users that were logged in will be registered who they were. All the files that were open, all these managers that will Windows have regarding all those files, there will be recorded which manager or which handler will be in charge. Because sometimes we say this handler because there are some traces of the file, or maybe we have nothing. We will be more about the one who leaves, the one which leaves no trace. Other thing, important thing is all the network connection that were open in that equipment, and information about the process that had opened it and through which port and everything. Furthermore, as it turns out that the system sometimes releases resources, there has been a process reading from a socket, reading network packages, and those packets have been released, or they were released from the memory. Actually, that free is just removing the hotspot, the spotlight from the object, and afterwards in a good system that has a trash collector or a good program in which they remember to do everything well, in the end, that memory should be turned back to zero at a certain point. It should be freed and restarted. That's what I say. That's what I say here. Some certain operating systems, for like Windows, when you release things, it's not restarted. Well, this is a vulnerability when you don't remember. I don't know if you remember when WannaCry happened. Because of this, they were able to recover the encryption keys in systems like Windows XP. Because when the object is released, the object that kept the keys was released, the key stayed there in the file, and they could recover the key. How do we analyze the memory dump? With volatility or recall? Those are de facto tools in this industry. I'm going to focus on volatility because it's the de facto standard for to analyze memory dumps in forensics, in computer forensics. Volatility is a tool that was released in 2007 by the name of Volatools in GitHub from the United States. It comes with an GNU GPL version 2 is open source and currently is maintained by Volatility Foundation. It's implemented in Python and something which is very good. It has an API that is awesome. It has a very good API that is very documented, in which if you want to implement something, you can do it. Apart from that, they support Analyze for many operating systems: Windows, Linux, Mac, the main three operating systems in the desktop computers, both for 32-bit and 64-bit edition. For each version, we'll have a profile. Everything I'm telling is from version 2. I don't know if you are aware that the version 3 has been launched in October last year. It's still waiting if they release it or not. But Volatility version 3 will come with Python 3, so it will be a very good change, a very significant change. Everything that I'm presenting now won't be valid. You will have to redo it again and all that things.
Of course, I am talking about malware analysis. Do you know how you analyze it? Alan is here, I'm sure he knows. So, what it is we try to determine what's the malicious activity that a potential application is performing in our system. We can do either a static analysis, which is called cold analysis. We analyze the executable files without executing them. We analyze the binary files. And as Aran was saying, we just look at the data, say, yeah, there's a mistake here, etc. But if we're making a static analysis of a binary, we are looking at all of the rejection pathways, and that would be great if we had all the time in the world, but this is actually endless. You're never gonna be done. So in computational terms, you're done. But the dynamic analysis is different because we analyze the executable under execution. So we will see what the interaction of that binary is with my operating system. What does it do with the register, with the files, with other processes, with the network, and with that I get an overview of what my binary is doing in the system. And the problem of dynamic analysis, which you're already thinking about, is that you're only analyzing the path that's now being executed, and that path may be derived from the environment conditions. The time, maybe the malware, depending on the time, takes a path or another one, or the number of users, the input. So we might be getting a biased view of what this binary is doing. So nothing is black or white here. This is the only image I have done with LaTeX. I'm going to do a demo with a Windows 7 86 machine, an Alina malware. You might complain because I always use the same one, but it's just that we've become friends. And it's slightly modified for local connection and with file systems. System files, sorry. So this is the program. You can see it well, yeah? So this is the malware. Alina rooted Alina. I'm going to launch this malware and I'm going to let it run and I'm going to use the machine and then do a dump to be able to analyze it. So I'm going to launch it and there's something which is very typical, which is it disappears all of a sudden. And you'd say, where's the binary? But then you go down, you click again, and that's it. No problem. So this is going to be running here. I'm going to pause it so that it doesn't use up too much battery. So before I start telling you about the stuff, we need to go through some backward. We've just heard a very interesting presentation about how mobiles connect with the modern protocols, and I'm going to give you a bit of background as well. First of all, the header, welcome to 1981. The PE header, this is the format of an executable file in Windows. It's called PE, Portable Executor. I won't go into detail, but it's just for you to know this is how it is, okay? I also want to tell you about how we create a Windows process. This is very important. You think I've just done a double click and it's been magic and the process is created. What's going on beneath? Well, plenty of things. We can define 7 steps. First, Windows will validate parameters. It will take the flags internally overlooked and convert them so that the system can understand them. It would do its own thing. Later on, it will take that file and map it in memory. Then it will create an internal structure, which is called eProcess, that comes from a Windows Executive Process object, which is the structure that's going to represent the process within my operating system. So in Windows, a process is nothing but a thread container. So the next step is actually to set up that structure of initial thread, which is called eThread, which is Windows Executive Thread. It set up its stack, its context, and it will fill up the fields in the right way. Then it will take a few more steps, sort of getting everything ready and organized, the parameters in whichever way they need to be, creating the specified memory. And then we will start with that execution of that initial thread, unless there is the process with a special flag, which is the create suspended. So before we start with the execution of this initial thread, is that in the context of this new process and new thread, this is already in the memory of the current process. The initialization of the memory space of the process will be made. So all of those libraries that are associated to my binary are also going to be loaded in the memory together with my process, okay? If you want to see this more visually, here it is. So we are here in the kernel, this is in Windows subsystem, and here in the process memory. Of course, we're going to be talking about memory, ladies and gentlemen. So let's talk a bit more about memory. What happens with memory? Or rather, how much memory can a process reserve in Windows? Well, by default, if we're talking about a 32-bit case, it's going to be 2 megas until Windows 8. This can go taken up to 3 or 4 under certain conditions. And if we start dealing with 64 bits in Windows 8, after Windows 8, the default size is 128 terabytes. But if you have a computer with this size of memory, let me know. What else is the memory manager, the window memory manager, going to do? It has 2 main tasks. And you'll say, well, but if I have 2 gigas for each one of the processes and I have 20 processes, how is this possible if my memory actually only has 8 gigas? Well, it's easy because we're talking about virtual memory. So the process believes it has its sort of partition area, but there is the memory system that makes the transition between physical memory and virtual memory. And it also performs an important task, which is because you do not have 40 gigas of memory, so when you no longer have memory, some of those processes will go to Visco and will continue with the execution, and when the process needs something, we'll recover that memory from Visco and we'll keep on working. Something important that you have to know is how is the memory granularity managed in Windows. It is managed, it's what we call memory page, which is finally a contiguous block of virtual memory with a fixed length. We have two types of pages, the small one for Ks, which is the more common one, or a big one from 2 megas to 4 megas, depending on the architecture. A memory page will be in different states. Okay, it can be free or reserved, and in those two states or status, reserved means that the process has told the system that it wants a new memory page, but it's not going to use it yet. Free means that we can use them all. And committed, I don't know in Spanish how you say committed, but we can use the English word. It means that the process can use it. And this is what we also call private pages. So from a free page, we've moved on to a reserved one, and finally to a committed one. And you have it in green, the one that's available for the process, and in red, the ones that aren't. And you can see the Windows functions here that we can use to move from one page to the next. And from free, we can go to committed if we call virtual alloc in a specific flag, but whatever. And finally, something else about the window memory subsystem and page files. When some of these pages are not used, they are written to disk. But how many pages are going to be written to disk, and how much do they take up? Where are they written? What's the result in? We can end up with up to 17 files, paging files. The maximum size could be up to 16 terabytes. That's about, and what will contain this file? It will have the memory processes, so it can have a memory of a user or of a process that was in kernel. So, due to security reasons, the content of these files, once you turn off the computer, is going to be cleaned up. It's going to be eliminated. The data, potentially sensitive data, are going to be removed. But this behavior is by default disabled, so you have to enable it. And I was reading this book just the other day. There is a new file with Windows 8, which is a swap file, which is for the applications of UWP. You've heard about them. That looks so nice with that display. And there's a single file with a specific size. Okay? So I've given you the background, so you know how Windows works and how to manage it. So let's move on to challenges. This is my machine. I have launched the process. It was running. I've paused it. So I write a script. I'm going to delete it. So now it is capturing. I will show you the script later on if you don't believe me. What I am doing here is to get the Alina process. Okay, because you do not believe me. that I don't know how to zoom in. So I'm calling volatility and I'm doing my stuff. So what it's doing here, first it has taken the Alina process. I found it out. I'm extracting it from here. And this is the malware that was running. And as it's being executed, it is going to stay there, copy itself somewhere else, and it will stay sort of executing itself forever. I also have the original binary. If I look at the MD5, what happens then? The MD5 of the original file is here, and the one that I've just obtained is this one. Why do they not match? Well, that's normal. So what's going on? What's happening here? You have to think that a process is not an executable file. It's the representation in memory of an executable file, and that file is something that in the disk, and that's different from what you have in memory. Why? When Windows has opened this file and has mapped it to the memory area, it's had to do a few things. Among them, they resolve the directions of the functions, the addresses of the functions. We have a protection that randomizes the load in their addresses. So that binary has some bytes that are going to be different. They will have change, and that's how it is. That's what we call relocation. And it's there since the 90s. And there's something else. If the binary had a signature, imagine one signed by Windows without encoding. So what's going to happen when Windows loads the binary and checks that the signature is okay, then it strips that part. So in the memory binary, the part of the binary that we can have in the disk regarding the signature is no longer there. The relog section, which is the one that tells Windows how they have to change all of the pointers, everything to do with positioning independent from code, in memory, we will not find it either. And there's another problem. I've told you that the granularity of the pages in Windows is 4Ks. So when Windows does a mapping of the file from disk to memory, it will map it to 4K pages. That is how it is. This is the situation I'm going to have. Usually, we have all of the headers of the PA will fit into one page, and all of the sections, each one of the sections will be in 4K pages. Okay? So far, so good, yeah? This is the relocation. So how can we try to solve this? Well, very simple. Rather than using hashes-based cryptographic hashes, SHT1 or 256, we can use other hashes that are based on approximation algorithms. So matching by approximation. We have in the group developed process fuzzy hash, and we published it a couple of years ago. And we are also adapting the P file, the Python P file, for it to be able to treat the binaries achieved from memory rather than the ones you have in disk. It's basically about changing some of the internal structures. And we will release that soon, but the other hash we have already published. This is very simple. Rather than calculating the cryptohash MD5, you just calculate the hashes and check if they are similar or not. The approximation algorithms are trying not to find a 0, 1, but a percentage. So tell me in percentage terms how similar this is to this. So this process fuzzy hash that we have implemented for volatility integrates for different algorithms. It's like an interface, and below we have 4 algorithms for approximation algorithms here listed. We have implemented everything so that everything can be extended. So if you want to implement some other algorithm or support for another algorithm, it's really simple. And we sent that to the volatility official contest, and we lost. But we are in the official branch of volatility, but we also keep our independent volatility branch. This is how it works. I won't give you too much detail because we won't have time, and the other stuff is more interesting. This would be one example of the output, the plugin, the dump, and for each PID or for each process, it shows the sections and their hash. And the problem you have here is that this is very long, but that's it. So this is the hashing phase, and this is the comparison phase. So what we see here is that we can have hashes from different processes, from different locations, and here we see the percentage of similarity, 94%, 100%, etc. So let's move on to the second problem. I've done a color div between Alina and the file that I have obtained, and I'm looking for a pattern that I want you to see. Not this one. Not this one. It takes a while, but it's coming. I promise you it's coming. I'm gonna add a few more zeros, see if we can find something earlier. Do not worry, I know where it is, but I just don't want to use the mouse because it won't look so good. So what have we got here? Lots of zeros, but this is of no interest. I'm going to do the same thing, but with a DLL, because this happens sometimes. Everybody knows kernel 32. It's in all of the Windows operative systems. It's like the crux of the matter. And this one cannot fail, because otherwise my demo is in trouble. Okay, there it is. So what happens here? In 2800, what a coincidence. Here we to the right, the real one, and to the left, kernel 32 from the memory. So here we just see zeros, yeah? What's more, we are moving through different pages, and there will come a time when to the left we will see code, where we will see code both sides, yeah, to right and left. So what's going on here? What's going on is that maybe my process hasn't used certain memory pages, and therefore they've been paged or paginated into the disk. And what happened to the one in memory? Well, it's not there. The page swapping is going to have an impact on this memory capture, and that is a problem. This can be due to the page swapping or due to the lazy page loading or demand paging. The process will only load memory when it needs it, and otherwise, why should it load it? It's there in the disk, and until you need it, you don't bring it. So, and that can have a negative impact on our memory captures. About solutions, we have some ideas, but it's ongoing work, so I won't talk about them here. Okay, so we still have a problem, and that is, how do I know that the information that I have received is trustworthy or matches the real one? You don't know. You have a problem when you're making a memory capture, particularly on a live system, and that is that memory in itself, it's a live system. So how does the memory capture work? Well, you start on 0 and you finish in FFF, and how do you know when you're reading here something earlier on hasn't been modified or something later on? Nobody can solve that. We have a problem of lack of consistency or page spreading. So throughout the acquisition, the memory can change so that your memory dump is inconsistent. It can, you are with volatility, with the tool working, and then all of a sudden it says that memory is not there. It should be there, but it's no longer there. So how can we solve that? There are options. You could just throw liquid nitrogen to the memory and that's it. Then it won't change. And the second one would be to try to force a crash down, a cartel panic, so that the whole memory is dumped. That can, however, invalidate evidence capture, and maybe that type of solution is not of interest to you. Another solution that we can attempt is to try to check the temporal consistency. And here we introduce the concept of temporal forensics. That's not ours. People from David de Lanzarote have done that. They've introduced the concept of temporal forensics. And knowing that this memory is going to change in time, they have done a plugin for volatility. And you can see it around if you give it a memory dump, and it tells you roughly the parts of the dump that may have been modified during the acquisition. So it does the checking of that capture, and that's great because it allows you to see if there is inconsistency in your dump or if it is a lack of consistency that you can live with. More things. Most of malware today uses persistence by means of registry-based. And in Windows, the registry has keys in the disk and volatile keys that only exist in memory. And because they exist only in memory, we have the same problem in that dump. Precisely the memory page where you have the key of the malware that I was interested in has been paged to the disk, and it's not there.
What we did here is to implement a plugin with its witness app. You have it around here. It's in the end of a publication, which detects, analyzes an memory dump and obtain all the keys. I'm going to show you how it works. The same dumping from Alina, and here I'm obtaining all the possible points, the starting points of the record that have been detected in the memory dump. This is not an exhaustive list. Besides, if it's something weird, it just displays a warning, an alert. We see what we have. I will let it running. It can detect if there's a suspicious pattern. It monitors app data. It monitors the most common keys. Here I'm telling you more or less what it is. You can download it. Everything that we do is GNU GPL version 3. You have the paper if you want to read more about this. As I won't have time, I'm going to tell you quickly. This is the classification that we did of the all possible starting points in Windows. So all those points that malware can use to self-initiate at the next reboot. And we analyze the permissions that you need to put there, to be there. And if you can detect in memory forensics analyze, because some of them are impossible because IR belong to the disk, and if you don't have the disk, you can do it. You can't do it. Okay. Before I said that the advantage of using memory dump is that it will be useful to get that initial triage, just to separate one thing or the other. This is good because in the end, if you can tell the analyst, instead of focusing on in these 450 process in this memory dump, go to these 3 precise processes. So here, actually, we could try to apply methods like Yara rules regarding dumping, and it displays an alert if it finds something. It's not useful to see if the malware code has been injected in a process, if there is a memory page that has dangerous code. But what happens if the memory page in which malware was, imagine there's a process that injected code in a legitimate process, but now it's not running at the moment, and Windows says, okay, you go to disk. So what happens to that analyze with the dumping? That you eat it. It's useless. You won't see the malicious code. That's something that we have to assume. Here we have created a small implementation, which is quite stupid. Maybe you know this malfind from Volatility. It's a plugin that it comes which detects malware. I send it to Alina's dumping that I have around. So let's go into have a coffee. It shows things like these. It says, okay, certificate host is dangerous. And who else is dangerous? Explorer.exe is dangerous. That's true, but not at the moment. This is not malware. So we did a little improvement, which is malscan, which we run malfind and run Clama V. But Alina, which was running in that scan, hadn't detected it, but with our thing, it does. Even if it's easy to detect Alina, but I swear, you see there? The output is the same as malfind. It's quite similar, and we obtain the tag that says that Clama V detects. We have detected this process. It seems to be Alina. We haven't published it yet because it's not solid enough for the moment. This plugin is integrated with Clama V. It only works with Linux. We are integrated with a daemon. It has 2 working modes, with the normal mode and full scan. The full scan will analyze the whole memory, looking for those regions which have X permission. All those permission, writing and reading permissions, and all the regions that are like bad regions, internal things of system memory management. I already told this. We also look for typical detection. If we find some code that could be the start of a function in a memory area reserved for a process that can be weird, and so on. And we are not done yet. I'm sorry for you. But here life goes on. We have more problems, such as hibernation file Windows file hibernation files. How do you analyze that? With Windows 10, we also have bigger problems. Windows 10 now, the page files that we kept into the disk when we did the swapping are compressed with the software, with an algorithm that we know, which is Microsoft Express. It's already known, but it's compressed. It's a very interesting talk about this in this year in Blaja. It introduces device guard, what happens with PowerShell. I tell you, in the moment PowerShell you do an exit, there's nothing in memory, so you won't be able to take anything. Also, we have missing the definition of profiles for memory acquisition in Linux and Android systems. There are many Linux distributions or Android that are not supported by volatility, but we still need to define that profile. iOS, we could even say nothing. Chromebooks, IoT devices, memory forensics world is interesting. There's a lot to do still, and there are more problems than solutions. Actually, we are just aimed to keep working. So, as a conclusion, I want to show you which are the main problems that we have in memory forensics. We have the problem that in the end, remember, then an accessible file in a disk is not the same as the process of that executable in memory because of Windows loaded, everything that will be done there. We have this incompleteness because of page swapping and demand paging. We have the problem of inaccurate data dumps. If we are retrieving the memory from a live system, we have the problem that Windows registry contains volatile data. Therefore, we can find some trouble there. We have a lot of memory artifacts that could be used, but we are not using them. And other things that are unknown yet, but that are actually there. For instance, now Windows 10 has brought, maybe you have read about it, all the Linux core incorporated in Windows, which is Windows WSL. This is supported by volatility, and your case had included plugins to work with this new process because they are not traditional processes, they are another kind of processes. So we keep advancing. We also have a lot of challenges to face. So what do we need here? We need people, money, and time. But that's always the case. The best thing of all, and the idea that I want to transmit, is that you can program your own plugins, like Abraham did yesterday. He presented something and published it. We can do things and publish it. We have to share. Sharing is life. We have to share with the community and give what we have received. And well, we have some useful references from the articles that I have been mentioning over the talk. There are articles if you are interested in memory forensics. Our articles, you don't need to read them because I can tell you. But the rest, you should read them in your header or next to your bed. I also want to finish with a sentence from Bette Davis, which is the less beautiful girl in Naked Eva. If you haven't seen it, I will recommend you to see this one. Afterwards, I will recommend you to see Todo sobre Madre from Almodóvar, and maybe you would understand it this last film movie. The key of life is accepting challenges. Once someone stops doing this, he's dead. If you have any question or any other thing, I will be glad to answer them. Hello. It doesn't seem too difficult for a rootkit to realize that someone is dumping the whole memory of the system and start deleting all malware pages that wants to protect. Do you know if rootkits do it at the moment? I don't know if they do it because I haven't checked that, this could be done. There are people who has done things about it to detect possible alterations, weird alterations. The way of storing memory internally in Windows, there are some structures which are called VAD, virtual address descriptors, VADs, and it's probably possible that if they are not done right, they leave some trace through VADs, so they can be detected. People had tried to do something like this with piles and with VADs. Thank you very much. There is an article, and if you want, I can send you the reference. If there's no more questions, we have a break until 12:30. In the central room, you will find something to eat and drink. We just beg you to be on time, because otherwise we will be late for the rest of the day. Also, we wanted to tell you that tonight there's a party organized by RootedCON. It will be in the BAT room in Tribunal.